Hey T's, how's it going? Mr. Cortez here, with this video that I made to introduce to you our motor station lab, our brand new motor station lab, and explain to you, what's going on in the station. What are all the wires? What are all the components? What is all this stuff that you're looking at, right, when you are sitting in front of the motor station lab? So, this motor station project that we have built here at Chula Vista, UEI, has been something that we've been working on for almost a year now. So we haven't had a really good, comprehensive motor lab at the program because it's difficult to put together something that's reusable, that's easy to teach, that's safe, and that's practical. So we've been developing this alongside the ET department with the help of our CDC and support from our management, from the director of education and assistant director of education. They've been supporting us and me in developing this station lab, right? So very proud to roll it out in 2025. And so I wanted to make this video for both students and for instructors to go over all the different components and me explain what's going on when you get to this class. Okay, so let me share my screen and we're going to go over a couple of things that I want to highlight from this. So first off, let me show a quick video of the actual station working. Okay, so let me share my screen with the video here and we'll share sound. So right here you can see the motor station in action. Let me play it again, right? So you'll have two power cords and you have plenty of outlets. Two power cords. One's going to be for the control power, and the other cord is going to be for the line power, for the motor power. Right? So that's where you see the two black cords coming in, and you'll have plenty of outlets on either side of the stations. And right here you can see it turning on and turning off. So you can see it works. We have also placed these guards. I don't know if you can see from the video. And place these guards over the shafts of the motors to make it even safer, right? Because when we turn these motors on, these shafts spin and it's pretty strong. The motors are have quite some power to them, so we absolutely want to make sure that we're being safe with all these things, right? So that's a video of one start-stop station working, and here's a video of two start-stop stations working. On, off, on, off. So you can see they work, motor works, right? And that's what this video is going to be about, how to understand what's going on with the wirings, how the labs are supposed to be conducted, and what all this stuff means, right? So first, let me show you a picture of the station fully built out. So this is, I would say, almost a 98% already completed. Let me share that screen. Right, so each mortar station will be the same thing. They'll have the same components, they'll have the same wiring. Each one will be the same exact one. We're going to build some more advanced ones, but that's going to be later on. We're just going to start with this basic layout, right? So from this layout here, I'm going to explain different things, right? What each component is, what to focus on, what not to focus on. So along with the stations, you guys will get three handouts, right? So you're going to get this handout that is a blown up version, a blown up diagram of the contactor. Right? And this is the contactor right here, right? So it's going to explain to you and it's going to show you what the internal wiring is and what the wires coming out of this contactor are. You're also going to get a handout that is going to show you the layout of the station, right? So if we look at the picture right here, You can see, trying to get them both into one right there. You can see, right, start stop A, start stop B. Right there is the contactor. Right there is the motor. This is a single phase motor. The blue ones are single phase. Right here are all these little parts. That's where the 8-pin base with timer relay right there. Right here, you see the 24-volt transformer. That's this guy right there. Then you see load 3 fan and the lights, green light and the red light. Okay, so that basically this is just a layout of what you're going to see in front of you. Right, you're also going to get um, some more information on the start stops, right? So you see these wires coming out of here, right? So station A will have 3 wires coming out, and this diagram will show you how they're internally connected, right? So wire 1 comes from terminal 1 inside. Wire 2 would come from terminal 2, right? That internal connection right there that we see. So there's a little jumper wire that's connecting to terminal number 4. That internal connection is only on station A. Okay, and I'm going to explain a little bit in the video why we need that internal connection only on A. And then wire 3 is from terminal 3 on the station A start stop button. Okay, so station A and B are going to be wired differently. And why they're wired differently, again, we'll get into that in the video a little bit later on. Station B is going to have 4 wires, right? So first one is to 1, 2 is to terminal 2, 3 is to terminal 3, 4 is to terminal 4, right? So in real life applications to control motors and groups of motors, we use these start stops to achieve that control, right? We don't use single pole switches or 3-ways or anything that's not a momentary, but a stationary contact, right? So we don't want single pole switches controlling these motors for many different reasons, right? One of the reasons is for safety. If we had a 480 volt motor, we would need a 480 volt single pole switch. And if we have that voltage on that switch, if anything goes wrong, then we can expose a worker to some very dangerous voltages, right? So what we do is that we use, through the use of transformers and relays, we lower the voltage down to have 24 volts, in this case, 24 volts or lower voltages to control high powered loads such as motors or lights, right? Um, so we've developed over time a system of logic process of ladder diagrams to be able to achieve that control. So we don't use stationary switches. We use these momentary start stop buttons, right? So these momentary buttons, when you press them, they will activate their function, but when you release them, they go back to normal. So they're only temporary, right? They're only while you press them and then you let it go, it goes back to its original state. Okay, so all stop buttons on a start stop button are internally wired as a normally closed button, right? What does that mean? So the key things to understand when it comes to motor control, and really any type of control, lighting control, motor control, um, is going to be normally open and normally closed, right? We see here that stop buttons are normally closed buttons and start buttons are normally open buttons. What does that mean? It means that the stop buttons, right, the 1 and the 2, so inside this little box here, you have a little screw that's labeled 1 and a little screw that's labeled 2. So when you don't press this stop button, those 2 terminals are normally closed. They're normally connected together, right? Until you press stop and that momentarily disconnects 1 from 2. And then when you let go of the stop, it goes back to connecting 1 and 2 together. So all stop buttons in motor control are wired in series, and that means that they're going to allow current to go through, and all stop buttons are normally closed buttons. Okay. All start buttons are the opposite. They are normally open buttons. So that means that normally the terminals 3 and 4 inside this are not connected inside. There's no connection made between 3 and 4 until you press start, and that temporarily connects 3 and 4 together. But as soon as you let it go, that becomes open again. Right? So all start stop buttons are going to be like this. Any stop is a normally close, and any start is a normally open. Okay, so alongside with this, let's see what else you get. You also get a student copy of the wires and what's going on in these stations. So let me explain a little bit about what's going on here and what we should focus on and what we should not focus on. Okay, so let me blow this up and so I can do a little bit of markup here. So with these stations, right, what we want to not focus on too much right now is going to be this part right here. So these two lights and the fan, those are yet to be integrated with our labs that we're developing. We have them there because we will be using them, but right now we don't have the logic and we don't have them integrating with what we got so far. So don't pay attention too much to these yet, right? And all these are is just two lights and a fan, and you can see the hot wire and the neutral for each one right there. So you see the three um, the three pairs for the three loads up here, and these are all 120. Another thing I don't want you to focus on is going to be this portion right here, the spin rail with all these little contacts right there. Again, we don't quite have that fully developed yet. We put it there because we want it there. It's going to be in the future, and maybe you guys can help me develop it more with more suggestions. But for right now, that's just up there for future use. Same thing with this little selector um, switch right there. Also, don't focus on that too much. So anything in blue that you see highlighted, we're not worrying about right now. We're not going to work on it. We're not going to do much with that for right now. The rest of the stuff, let me see if I can get a different color for this here. No, not filter, markup. So how do I get a different color? Oh, here we go. So let me mark some things in red. So the rest of the things, this portion right here that we want to focus on, that's important, right? So right here, this power cord is our 120 volt in. This little device right there, that's our transformer that will change the 120 to 24 volts. 24 volts, right? So from the four wires that we see here on the right, the black and the white are if you have 120 as your primary. The brown and red is if you have a higher or a different voltage, 208 or 240. Since we have 120 in the lab, we're going to use the black and the white, right? So when you plug that in, then the transformer will lower the voltage down to 24 volt, achieving that safe voltage, right? 24 volts is a lot safer than 120. So that's what we see here. The blue and the yellow are the 24 volt out, right? So what we see right here, and let me draw along so you guys can see the blue. And again, these little terminal blocks, they connect across. So whatever wires connected across from each other is the same wire. It's like if you were to make a splice. So we follow this, this goes around here and it comes back. And the 24 volt hot is this blue. Oops. Oh, I did that. So right here comes back down and that's your 24 volt hot right there. The white one is going to be the 24 volt neutral. That goes back down here and right there. So that's why we have this blue wire coming down and this white wire from there, because those are the 24 volt from the transformer. That's your power source, 24 volt. Right. So let's see right here. Let me continue on in red. Another portion that we do want to pay attention to is going to be the start stop buttons right here. Right. So right there, and again, to just be very clear as far as what the internal wiring is, what's going on there. You can always use this as reference, right? And I'm gonna give this to you guys for lab when you have this, so you can trace and you can see what the wires are and what's going on right there. So let me see here. Trying to zoom in. Kind of not letting me right now. Okay. So I wanted to zoom in and you can see right here, 1, 2, 3. It's a little hard to tell from the labels, but I did label every single wire on each end. So that's 1, 2, 3, and that's 1, 2, 3, 4. You can see we have 3 and then 4 right here, which is what we see from the drawing. 3 wires and 4 wires, right? So these are, I think I label these 1A, 2A, 3A, and this is 1B, 2B, 3B, 4B. That way you guys can understand what those wires are. Also, what I did was I had and I grouped those wires together so they're easier to identify, right? So right here, this bottom group of 4 is this group right there, and they're under one wire uh, tie wire. And then the 3 from station A are these 3 right there. And again, at the end of these, you'll find them labeled. You can see right there, 2B, right? This one's 1A, I believe, right? So from the ends of the wires, everything's going to be labeled telling you what that is, where that wire is coming from, right? So let's go back here. So that takes care of the start-stop stations. That takes care of the 24 volt, right? Now we'll get into the contactor, which is probably one of the hardest parts to understand what's going on with the wiring. So from the picture, it's a little hard to tell what's going on with the wires and what's going out and what we're going to connect to. So for that, I also provided a detailed page explaining what those wires are. And so let me move them side by side so you guys can see that it's accurate to what we have wired in there, right? So starting off with these wires here on the left, 1L1, and you can see right there it says 1L1, right? That's going to be your 120 volt power for your motor. So that's your hot, right? That's your constant hot. L2 is your 120 volt power for motor, but that's your neutral, right? So then we see that. That's your neutral. So that's your hot right there, that one, and that's your neutral, right? And they're labeled L1 and yep, this is L1 and L2, your neutral. So right here you can see L2 right there. So this is L1. So again, L1 is your constant hot, L2 is your neutral, and that provides power to your motor, right? That's your 120 volt power for the motor that we're going to be turning on. Next wire is going to be this wire coming up here, 3A1. And so that's one side of the coil that we need to activate this contactor. And on these contactors, the coil, it's a little hard to tell from this picture, but the coils are rated 24 volts. So we cannot put 120 in the coils. And if we put 120 where it's rated only at 24, it would burn up the coil. So the coil is rated for 24 volts, but the actual contactor is rated for much higher voltage, right? So it can definitely withstand 120 and even higher, right? And where the line portion is on this contactor is the L1, L2, and L3. Okay, that's the line portion. So in those 3, those can take quite a bit of voltage, but the coil, A1, A2, and 13 and 14, those are all just 24 volts. So that's what 3 is. And we see here that blue wire is 3 right there. So it's labeled 3. 14 is going to be 2, and that's your normally open auxiliary contact. And that's where we see this wire right here. That's 2. You can see right there it's labeled 2 as well. So that's that second wire. That's 2. I'll explain with the ladder diagram why we're wiring like this and why we have it set up. The next is going to be this internal connection. So you can see this little wire, this little jumper, right? And that's what this is. So behind that 14, it's hard to tell from the picture, but in the contactor, there's a little screw that's labeled A2. And so there's another screw up here that's labeled A2. So those two A2s, you can see right here from the diagram, they're internally connected. So that's one side of the normally open contact. and that's the other side of the normally open contact. And so that is what's connecting right here to 95, right? So 95 from 92 to 95, right? So, and what this bottom portion is the overload, right? So what a motor starter is basically a contactor, which is just this top part with an additional overload protection, right? So a quick explanation of that is when it comes to motors, we cannot just put a regular breaker to handle short circuits, ground faults, and overload protection. The reason is because a motor, when it first starts, has a very high inrush current that it draws. So it can be up to 3 times the amount of the actual rating of the motor. So if you were to have a 20 amp motor, let's say, when it first starts, it's going to pull in 60, almost 70 amps, right? So if you just put a regular breaker and that breaker is rated for 20 amps, which is what the motor is rated, then the breaker would never let the motor start, right? Because it's going to think, oh, I'm rising past my 20 amps. I'm going to kill the power and I'm going to trip, right? So it would never let the motor start, right? So we still have to protect against short circuits and ground faults, which are very high current faults. But the overload is something that in motor control applications, we separate from the ground fault and the short circuit. What do I mean by separate? Is that we're gonna size our breakers higher than what we would normally size, right? Because we still want to protect against short circuits and ground faults, which can be hundreds of amps in a split second, right? A short circuit is a fault that's between any phases or a phase in a neutral, right? That's going to immediately cause a high current rise. And so our breaker, if it's rated at 70 amps, will trip and protect the equipment. Same thing with a ground fault. If a hot wire touches something metal that it shouldn't, that's going to cause a short circuit. And again, the amperage will be rising up really quickly, and the 70 amp circuit breaker can protect against that, right? The problem is with overloads, right? Again, we want to make sure that we still protect against overloads, right? As the motor is running. So an overload, for example, could be that the motor is running fine and you have a conveyor belt that's attached to the motor, but you put too many boxes and it's too heavy. You're overloading the motor. We still want to protect against that, right? But how do we do that and not put a standard breaker, right? So that's where we use these overloads, these additional attachments to regular contactors, right? Regular contactors would just be this top portion up here, and they use the principle of normally open and normally close and the coil to control devices, lights or motors or anything, not motors, lights, right? Contactors. With the overload protection, what we're doing is essentially we're creating a way to still protect against the overload because this overload device knows that it can allow for short periods of high amperage while the motor starts, but any overload after that has to be cut off, right? Because you're overloading the circuit. You could damage the motor, you could damage the devices. So this overload, all it is basically an amp meter that's constantly measuring how much current is running through it. So once it senses that after its initial inrush, once it senses it's being overloaded, then that overload will kick in and trip, right? Um, so that's why we want to connect our coil to this overload to integrate to be able to protect against that overload in a separate way, right? Motors are the only thing that does this. Lights, and heating elements, anything that's not a motor is just going to be protected by, like if it's rated 30 amps, you're going to get a 30 amp breaker. Motors, again, are the only thing that are different, right? So in order to understand this a little bit better, let me see. And so what we see actually, before I get into that, let me explain and finish explaining the wires here. So what we have here is number two, and that would be wire number two. The second one is your normally open contact, and 96 is your neutral for your control circuit. So that's why we have this last one, and you can see right there it's labeled 96, right? So in this overload, 95 and 96 are in normally closed contact. So that means normally, if the overload has not sensed an overload or some fault, it's connected normally together, 95 to 96. So once it senses an overload, it will trip and change states. So it will stop allowing the current to flow from 95 to 96. Okay, so again, in order to explain that and understand that a little bit better, we have to go over ladder diagrams, right? So ladder diagrams are how we interpret and how we understand these advanced control systems in the field, right? You're not going to get drawings like you see, like the drawings I'm showing you, right? You don't get drawings like that. They're not that explanatory. They're going to be ladder diagrams, right? So I took my time to draw those circuitry out, all those drawings, so you guys can understand, but it's not going to be seen like that. You're going to see ladder diagrams in the field. So we have to learn to start interpreting these ladder diagrams, right? So it helps not only with motor control, but if you're interested in PLC, which is really exciting field, um, that's key, is to understand start, stop, and to understand a ladder diagram. So what a ladder diagram is, it's basically a graphic representation of the logic that's going on in this station. Right? What does it mean by logic? Logic is the flow of current. What are we achieving? What are we doing with this electricity, with this setup? Right? It's a process um, diagram, basically. It's telling you if you press this and do this, this will happen. Right? So in order to further illustrate that, let me grab this, get paint. Now I'll draw as I explain what's going on in this ladder diagram. So with this ladder diagram and all ladder diagrams, you'll always have an L1 and an L2. Okay. And so what this ladder diagram is a ladder diagram of the 24-volt portion, right? Not the line portion. So L1 will always indicate your hot, your constant hot. So right here, and let me draw that by drawing red. So this is your constant hot. So this is your wire coming out to your constant hot. And so remember earlier when I said that your stop buttons, you always want to connect in series, right? And that's what we're seeing here. Stop is connected in series, right? And your starts in parallel. So right here where we see 2 and we see that black dot, what that is a wire nut. That's a wire nut. And from right there, 2 wires are coming out, right? One to one end of the start and one to one end of the coil of the holding contact, right? Then we see 3 goes, this wire named or numbered 3 is coming from the other side of the start and also splicing together, and they're going to A1, right? A1 is the coil. Right? Remember when I said earlier, this top portion is A1 and that's your coil. That's what we're seeing right there. A1 is your coil. Then from A2, it goes to 95. Right? 95 is again this bottom portion, right? So A2, that A2 that we can't see in the back, that's that wire connecting to 95. So that's what we're seeing right here. A2 to 95. And then the OL, that's your overload. And you can see that's a normally closed. So that's the internal connection from 95 to 96. And from 96, you go to your, just like with any load, anything electrical, that's your neutral. So this is all, again, the 24-volt portion of it. And so what's happening here, let me explain the logic is and why we're doing it like this. So again, remember I said we don't use single pole switches and anything that's stationary. We had to figure out a way, and what I mean by we is electricians and scientists and electrical engineers had to figure out a way how to be able to control these motors from these stations and not be a temporary type of device. And so how we do that is by using more contacts, right? We use an additional normally open contact to essentially bypass the switching and create what we call a latching relay, a latching contact, right? What does that mean? So when we plug in power to our motor station, right? And remember, this is all from the 24-volt section. When we plug power, we'll have electricity. Oops. We'll have electricity running on the hot. And right, and if we connect our stops in series, just like we see from the drawings earlier, let me bring up the, I have it here somewhere. We can see here that's the stop, right? And again, stops are normally closed, so this is connected across, right? And right here where we see this little splice where it goes out to 2 and it also connects to 4, right? What we're seeing is essentially this. We're seeing 1 connects to 1, right? Then 2 right here connects to 2, which would go to the contactor, one constant hot to one side of the holding contact, the holding relay. And then we see that internal splice, right? So this is constant hot, constant hot. We see that internal wiring go to 4. And that's what we see right here. This goes to 4. So really, this is 4 on the start stop. And that's 2. And then this is also 2. Right. So, and then 3, you can see it goes on the other side. 3 is independent, right? It's not constantly hot. So 3 will only get electricity once you push the start button. So what happens here is that, right, this start is normally open. Electricity is not flowing through here. So when you press the start button, you temporarily allow electricity to go through here, right? Go through this coil. And this M is associated with this contact here, right? So at the same time that electricity flows through this, it will change the state of this holding contact. So it will go from open to closed. So now electricity will also flow through here, group together and flow through here. And because the overload is a normally closed contact, flows all the way. We have a closed circuit. So now when you let go of the start, you'll lose power from here, right? But because this is now changed to a normally closed contact, you've created a bypass, a memory circuit that is holding the electricity, holding the contact, right? And until either the overload trips out and resets everything back to normal, you'd have to reset the overload, or until you hit the stop button, right? Because again, the stop is a temporary button. Once you hit the stop button, that resets power to everything, and it goes back to how we had it in the very beginning, where electricity is just waiting there, right? So what we're doing is basically creating a memory circuit. It's your most basic type of memory circuit because it's through use of an additional holding relay, a normally open contact, we're creating a memory for this circuit to remember you hit the start one, it will keep the power on, but once you hit stop, it resets everything. All right, so that's what we're seeing right here. And so the contactor is doing just that. And let me go to the drawings of the contactor so we can go over a couple of those. Contactor is going to be right here. So the contactor, right, the L1, L2, and L3 are for use if you have three-phase system. Since we have 120, right, we're just going to use L1, that's your hot, and L2 is your neutral, right? From the L's to the T's, those are normally open contacts. So normally it's not connecting the L's to the T's until we activate our coil, which is from A1 to A2. Remember that A2 could be either this terminal or this bottom terminal. Okay, so when you have the coil on, then the L's will connect to the T's, and from the T's is where we go to the actual motors, right? The actual wiring of the motors. And I'll have another video separately how to actually turn the motors on, which is fairly easy. 98, 97 is an additional normally open contact. We don't have to use that, and we don't have anything in use for right now for that, but we may use it something else. And so right here where we see the T1, T2, T3, or the 2, 4, and 6, again, that would be going out to your actual motor. right? What we see here, 13 and 14, through here, right, from 14 and 13, that's another normally open contact, and that's the holding contact. So right here, 2 would be connected, and that would have constant power on waiting until we press a start. Then we would have power connecting on 3 coming down, completing this circuit. Once you let go of start, then this would lose power. But because of this has changed states from open to close, now we have that holding contact, holding that electricity, holding that coil down until again we go to stop, and then that resets power to everything. Okay, so that's your basic start stop. And I'm trying to be as detailed as possible with all the wiring and what we're seeing here. And that's pretty much the gist of it. Let me go over just a couple more things as far as the grouping of the wires so you guys don't get lost. So again, the blue and the white are the 24-volt hot and your neutral. The groups of 4 right here, that's your 4 wires from station B. The group of 3 right here, that's your 3 wires from station A. The wiring from the T's, right? T1 and T2 are these right here that you see. Those are also labeled. They're connecting to the actual wires from the motors, right? And from this one, it's a little hard to tell, maybe from this picture. Oh, and then the 120 power cord is going up, and that's your 120 right here. So hot and neutral, right? And again, don't pay attention to these up here. We haven't done anything with that yet, and don't pay attention to that and the selector switch, right? So right now, your goal is to get familiar with this stuff and just first wire a single start stop, right? Once you get done with that, I'll have another video and we can go over 2 start stop stations because it does change a little bit in the logic and the ladder diagrams change, and I'll explain that in a second video. All right, um, so hopefully this is informative. Remember, with these motors, they can be dangerous, so please do not wire yourself in directly. If you're with an instructor, you have to make sure that the instructor is checking to make sure that you wired everything correctly. Um, and um, and let's see, anything else? I think that's pretty much it. So see you guys on the next video. Please let me know if you have some feedback, if these videos are helping out, or if you need a lesson on something else. I'll be doing a lot more videos for all students and all the ET modules. Okay, so thanks again, and I'll see you guys on the next video.